Yeah. In that context, I will cover some part of the top quark a little bit, and then the remaining part I will talk about the Higgs boson. Okay, so in particle physics, what do? We basically, if you just keep going like this, then at some point we can see the fly, and further, and at some point we hit the DNA structure, yes, and beyond that is atom, beyond that nucleus, beyond that quarks, which already talked about, and then if we expand it further, what's there? We don't know as of now. Okay, so what are we trying to address here? We are trying to address the very fundamental question that what is everything made up of, and what makes these entities to act upon each other. And we physicists are trying to explore such structures or dynamics in particle colliders, and I will try to explain how. Sanjeev has already done some part of it. Okay, so little bit of history here. So if I go to late 19th century, at that time we had something called Ruhmkorff coils. How many of you know about it? No, right? So those were the induction coils. With that, people could produce some kind of with the DC obviously, and some kind of induction coil, and with that they used to generate the higher and higher voltage. And then Crookes used that high voltage pulses to discover the cathode ray. This probably you know. And what is a cathode ray? But at that time, the cathode ray was known to have the deflections under the electric and magnetic field. So this is just an illustration there. And so this gentleman, Thomson, in 1897, he studied in some chamber, the closed chamber, the properties of the cathode ray. And what he did, you know this experiment, right? There should be some animation, yes. So sorry, I was missing it here. It goes straight if I do not apply any magnetic field or electric field. Then what he did was this. First electric field, obviously it will bend the opposite way. Then apply the magnetic field in the opposite direction. Now it's straight because it cancels out. So what is the summary? The summary is that the electric and magnetic fields cancel, and at the end you can calculate what is the E by M ratio by knowing the corresponding B and E, and obviously the radius of curvature. So Thomson found that E by M is 1.76 into 10 to the power 11. And while the ionized hydrogen, which at that time was known, that was something like 1,000 times heavier, and so he concluded that it has to be at least 1,000 times heavier, and that was the very first discovery of the elementary particles, dating back to 120 years ago. Almost, more than that. Then came this gentleman with his grad students or graduate students or PhD students, Geiger and Marsden. How many, some of you are masters or BSc, right? So there is, have you used, for example, this Geiger Counter? Okay, so it was named after him. So what they did was this experiment. I think Sanjeev already covered or talked about it a little bit, and now all of a sudden you will see some of the particles that bounces back, but that probability is very rare. And what it means is that you can think of it's like you fired a 15-inch sail into a piece of tissue paper and it came back and hit you. Because you can see how much is, I think both of them died. Okay, I have to change alternatively. Okay, gold foil has a thickness of something like 0.4 micron, right? So you can imagine that it should not be coming back, but that's what was found in the experiment. And at the end, this basically the bottom line here is that the structure inside the atom was revealed with this experiment. So then in 1930s, so there was a long gap. Then 1930s, after the discovery of the neutrons, a new puzzle arose. So what is the new puzzle? The puzzle is that the like charges repel and the neutral particles do not attract or repel. Now, what kept them together? That was the profound question at that time. And nobody has no clue. Then this gentleman came out with this nice proposal that there should be some kind of exchange particle, and that he proposed as, so this is proton, this is another proton, there are different kinds of pions there, and it exchanges, and this exchange continues, and that's why the nucleus is bit stable. And he proposed actually these three pions at that time with his theory, and he also proposed, or suggested rather, that we should be able to, if they exist, then we should be able to find these particles in the cosmic experiments, okay? And because there was no collider at that time. I mean, collider physics, accelerators were in the very early stage. I do not want to go into that. I believe there is, I think few people, they're talking about the accelerators, so I do not want to cover about that. But at that time, already by then, it was known that the cosmic rays, you have highly energetic particles, and there you can find such pions. Okay. So then, all of a sudden, Anderson and Neremeyer in 1937, they discovered a new charged particle with a mass of 105 MeV. And they initially thought it's just to cause pion, but what came out was that it's not pion, it's rather the muon that we know today. And it's identified, some of the properties did not match, and that led to, there is a whole bunch of story there. I do not want to get into that, but it was essentially identified that some particles which they then wasn't very well known, and they told that, okay, this is the muon or some other kind of particle. Then finally, in 1947, the real charged pion that Tukawa proposed was discovered in the cosmic ray. And what was the reaction, or rather decay? Decay is that any textbook in particle physics, I think you will find this picture. And here the pion decays into a muon, and obviously a neutrino, as we know today, muon neutrino, and then muon further decays into electron and two more neutrinos, and there are certain dynamics that has to be, or lepton numbers have to be conserved, and etc., and that's why it has to be two muons. There was other discussions or puzzle at that time, but people understood slowly and settled the problem. So they leave the tracks. Actually, these are the charged particles, so they leave the track. Obviously, the neutrinos will never leave any trace, and these are the experimental observations, and people interpreted that this is what they found, like pion entering and then decaying into muon, and then muon decays and two more neutrinos are coming out, and then electron. So that's how the pion was discovered, and this was already mid-40s, almost 50s at that time. And then many more new particles were discovered through the cosmic ray experiments, and more than actually 300, is it visible? And such large number of particles basically tend to lend themselves to the classification scheme. And this is a bit historic in the sense that you can think of how Mendeleev organized. Yes, you can look at the literature, more than 300. And that time, if you look at the something called particle data group listing, you will find them. I have the full list. And also there is some repetition of properties, so that sort of hinted that there must be some kind of underlying structure, and that's why we get so many particles in nature. And then these two gentlemen, Gell-Mann and Newman, then in 1961, can you see it? It's very hard, right? This blue color, I do not know. I just took the color arbitrarily, which I could see on my laptop. But okay, anyway, so basically the idea was that they proposed some kind of isospin and hypercharge, and based on that, they could arrange all these particles, whatever was discovered. Isospin is like for example, the top quark is the isospin partner of the bottom quark, or up and down is isospin. That's another kind of spin-like quantum number you can think of, and that was required mathematically. Just like you can think of today, we are talking about the QCD colors, and when I think I will come back, it's the SU3. And here, isospin and hypercharged space, it forms the SU3 and etc. So that was just a mathematical number that was required there. Okay, so SU3 quark model, and today we call it SU3 flavor quark model, and that was proposed, and that hinted at that time with basically U, D, quarks and so on. And then everything was proposed in something called the baryon decuplet, and there was, what are the other things? Meson, what do they form? U, octet. Okay, there are also octets for, so this is just one which basically was the trump of Gell-Mann's theory, simply because he could find all the particles were observed except this bit over there, and that has to be there, and that was missing at that time. So Gell-Mann basically proposed that there should be a new particle. He gave the name like omega baryon, and then it was discovered right over there, and that's the next slide shows the discovery in 64. So within 2 years, people found really the particle, the omega is decaying, and so on. So that sort of gives the complete picture of the quarks up to U, D, and S. Okay, and by 64 that was established, and then later some puzzle came by then that what about the quark confinement? I mean, quark cannot be found in isolated free quarks cannot be found. It's always the bound state. For example, in the meson, you can think of this happens because so the color, it means really some kind of color, but it's called the color charge that we are talking about. I think Sanjeev was talking about it earlier. That this any meson or hadron, they're kind of colorless object, but the quarks they can carry color, and in fact you cannot if you try to detach two of the meson states, then so much energy is required. The energetically favorable scenario would be such that two more mesons would be created rather than keeping them apart. So this was the quark color hinting at that time. And then subsequently I did not go through the remaining one I listed. For example, the proton substructure was by 1968-69, it was established through the SLAC experiment, and 1974 Barton Richer and Samuel Ting, they found the J-psi particle, which is nothing but another quark bound state, like another meson, right? It's a CC bar, charm and anti-charm bound state. And then 1976, Martin Pearl discovered the tau lepton, which is the third generation, the first lepton at that time. And then next year, Leon Lederman, he found the bottom quark. So that already, so remember we had till 64, Gell-Mann's theory, we had U, D, S, muon, electron and neutrino, okay, two of the neutrinos. Then the whole bunch of the third generation that I'm going to talk about next was discovered afterwards, and this period actually in the 1970s, I think this is called the November Revolution or something, and if you just look at some of the science books there, at least in US they mention that's like November Revolution, because so many new particles, etc., etc. And in 1983 at CERN, the W and Z bosons, these are the mediators of the electroweak theory. By then, by the way, I did not go about the theory, but by then Salam and Glasgow and Peter Higgs already proposed about the electroweak theory. And Carlo Rubbia at CERN, he basically, and Simon van der Meer, he discovered the novel technique for stochastic cooling to cool down the antiprotons. Like antiprotons are generated. So if you think of like I continuously hit and new particles are coming out. If I know that new particles are coming out, that is of a particular nature, for example, antiproton, they will have different all sorts of kinematics, meaning momentum and energy. Now, inside the collider, if I want to collide them together, I need a particular energy. I cannot go with variable energy. So Simon van der Meer, he got the Nobel for something called the stochastic cooling. So then later, in 1995, CDF and D0 experiment at Fermilab, they discovered the top quark, and that was the end of the particles. So this is the summary. So you see electron was the first, then the photon, then muon, and this is what we know today after 120 plus years, all the particles, okay, that is discovered this. And meanwhile, by the way, in 2000, the tau neutrino was discovered by the donut collaboration. Where is tau neutrino? Here. The tau neutrino was discovered by the donut collaboration, and 2012 story that we are going to cover very briefly about the Higgs, and that will be later. Okay, so standard model explains all the results of the terrestrial experiments without any known inconsistencies so far, meaning nobody has claimed that standard model is wrong. But and all the particles that was supposed to be there, that is there, then what's the future? So this is, as it is today, the standard model, and our understanding that this is the first generation of quarks and leptons, and this is all the atoms are composed of these. Then you have the neutrino, this is produced in the beta decay. Then you have two more copies of the matter or fundamental particles, and these are obviously, this side is fermions, all of them are fermions. And then you have the force carriers or the gauge bosons. For example, W and Z, they are the weak force carrier. Photon is the mediator for the electromagnetic force, and the gluon is the mediator for the strong interactions. And then the Higgs was in between, by hand added to give masses to different particles. So this is our understanding today, and it requires a detailed theoretical framework which is known today called Standard Model of Particle Physics, and this is based on the gauge invariance and relativistic quantum field theory. So what about the particle masses in Standard Model? So top quark is the, I think both of them now died, or okay. The top quark is the heaviest one over here, and you can see the electron is here and the neutrinos there. By the way, neutrinos are in Standard Model. Do they carry any mass, or do they have any mass? No, right? Whenever you tell neutrino is carries some mass, that means it's a beyond Standard Model, is violating the Standard Model. Okay? Nowhere in the Standard Model is claimed to be the massive or carrying any mass. So, so just a cartoon. If you think that's the ant, and the top quark mass is the elephant mass. Okay? So then, and this is just stated the same way how the gauge bosons, they interact with the leptons and quarks and the Higgs boson, who are so remember, if I ask you now in the Standard Model, if whether Higgs boson interacts with these neutrinos, the answer is no, because the neutrinos are massless. So that means zero coupling. Okay, and in this whole game, in the current state of affairs, that's the Standard Model, the gravity is excluded completely. Why gravity is excluded?
Graviton is not discovered yet.
Okay, but any other reason that you can tell? Yes. So the strength of the gravity is way weaker than all other forces. And does anyone know what is the level? Like 10 to the power 5?
40.
Yes, that's right. 42. Okay, and another important feature here I wanted to mention, so that means as of now, according to the Standard Model, we have the atom here, carbon atom, then you have the nucleus, then each of the protons you can think of this way, and then they have the quarks inside, and we are trying to probe the things beyond that, and that's why we are at the LHC colliding. And one of the important points you should remember, all the hadrons and the mesons, they are colorless, but the quarks can be colorful. Okay, so are you at the crossroads? Then, so Standard Model is an incomplete theory. Why? All of a sudden, I was telling the good stories about it. Now, all of a sudden, what went wrong? There are other observations. Physics cannot say that, okay, I work only in this field, and this is where I do not find any inconsistency, and that's why this theory is supreme and it must be valid. I mean, it has to be compatible with other fields, what they see. For example, here we do observe that I'll go in a minute, that we observe only the matter. There is no antimatter, at least a remnant one that we do not see. We can generate, obviously. And so what was the symmetry, and we believe there is a symmetry between the two in the universe, but that's not what we see today. And then there is something called Higgs mass hierarchy that I think it's a bit technical, but I can come back later. I have some slides in the backup. Then you might ask the question, why only 3 generations of quark? And remember, quarks and leptons. I mean, we started with, let's say, if you go back 1950s and so on, it was less than 3, right? And people could survive and go on. And so why only 3 generations of quarks and leptons? And there is nothing standard model states about the hierarchy of the fermion masses. For example, the ant versus the electron mass. If I take it to be the ant mass, then the top quark mass is the elephant mass. And there is no explanation for that. And obviously gravity, we know that's the force, and that is completely ignored. And I mean, that's including the gravity, the theory would be something like the string theory, the quantum supergravity, and etc. together. And in addition, from the experimental side, I mean, these are the theoretical point of view. You can think of some of the lacunae. But on the experimental side, you can immediately see that there is no dark matter candidate. Why is dark matter, by the way? Why do you call dark matter?
It is not detected.
It does not reflect light.
So it does the electroweak, the weak interaction or strong interaction. Does it participate? It doesn't interact with anything in the standard model. That means, but then how do you know that it's there? That I will explain. But the gravity is something that is still there, and its presence can be felt indirectly that the mass is there. And then obviously there are strong indications from the neutrino oscillation that the neutrinos are not massless. I mean, they do carry some mass, maybe some small number, but they have some non-zero mass. So these are some of the experimental side convincing reasons.
What is Higgs mass hierarchy problem?
If you hold, well, I have some slides, but do you really want me to discuss, or I can go after my talk on that if you just hold your question for the moment. Higgs mass hierarchy is something like in the standard model that there are 2 large numbers. One is positive and one is negative. They are cancelling and giving the Higgs mass according to the current theoretical calculations. And this is
Positive?
let's say 10 to the power 19 level, some number. Okay, why don't I go directly? It's too much. Yes, so according to the quantum field theory calculations, you can think of the true Higgs mass is the number like this. Okay, that comes out. Now if I go further, so I think this is more appealing maybe. So you can think of this number. So Higgs mass is coming out according to the calculation. That okay, some number, big number over here, and you subtract and you get exactly the observed mass that we are getting, and it's very unlikely, right? I mean, the orders of magnitude you can think of, right? And that is what is called the Higgs hierarchy. What is n? N is some number, but in both cases they are exactly the same. Only the last few digits are different, and you subtract and you get the exact same mass which you observe. So which is not something you prefer, right? So this is where the hierarchy problem is there. But this is consistent according to quantum field theory, because there are virtual transitions that can happen, and you can can have such cancellation, but it's most unlikely. So that's why we're thinking that, okay, I mean, if there is, okay, so we all know about this story. This galaxy, spiral galaxy, the rotation curve. This is the evidence for the dark matter. So you know from the Newtonian mechanics that if this is spiraling, then you should be getting, if the mass is only the luminous mass that you can see here, you should be getting that curve. But in practice, you get the other one, and that is indicative that there is some mass which you cannot see, but gravity is somehow taking it into consideration. Okay, evidence number 2. So every galaxy has this kind of dark matter. So then the bullet cluster, this is the direct proof. So what happened here is this happened actually quite some time ago, and this is 3.8 billion light years away from us, and two of the clusters, the galaxy clusters, they crossed, and through now you wanted to know where is the mass concentrated to the two galaxies. So for that, and this is, by the way, a composite image. For example, Chandra telescope that takes the X-rays, and then this is the Hubble and Magellan telescope. So this is a combined image from all this. So the gaseous material. I mean, this is the center of the galaxy. They crossed, but still the gaseous material, they could not go into that region, and that's the indication that there is some material in between where it's still interacting, and and since it's dark, that means only gravitational force, and that's why they haven't moved it yet there. So these are the two evidences of the existence of the dark matter, and as of now we know only 5% of the universe. Okay, whatever we are doing, LHC, you, me, the whole visible universe, etc., only 5%. Rest 95% is completely unknown. I mean, this is the dark matter, which is 21%, and the other one is 74% dark energy. So where to go? So then where is the complete theory? Well, the theorists have to come up. I'm not a theorist, but I need to explore some theory, and theorists have thought many new ideas. So for example, some of which you may have heard of, like supersymmetry, then the extra dimensions and so on. And this is, I think, Hitoshi Muarama from Berkeley. He did it quite some time ago, and he just told that something we haven't thought about and something we haven't thought about, and etc. And so we are really in a puzzling scenario that there is no experimental evidence from the collider beyond the standard model physics, and we need to explore, and that's why we are at the LHC and trying to collide the particles. Okay, so how do you explore then? So you all know this picture quite well, that we need to explore over there, so we have no other choice other than LHC. By the way, where from do you get this one? Sandwich Island. This is what? This is due to the temperature gradient. There is some cold wave on the ocean that you can see, and for that, obviously none of the terrestrial telescope or anything will not work. You have to go to satellite and take the image from there, and indeed this is the picture from the NASA. So Sanjeev has already talked about it. I think the key word here is that E equals h nu, and this is the Planck-Einstein relation, and then using the corresponding de Broglie wavelength, which you can see from there. And that's why we do, so the key word is that the shorter the wavelength, the higher the energy. That's what we are exploring. So we have a gigantic machine that you have heard of. So, so this is Lake Geneva, and this is the Switzerland, and this is the French side. So part of the thing is at Switzerland, part of them are so CERN is over here. So CERN is also, this part is in France, and this part is Switzerland. Fortunately, the electrical plugs are not identical across this site at least. So you have the four experiments, CMS and Atlas. These are just diagonally opposite. This is 27-kilometer ring, and then Alice and the LHCb. So these are CMS and Atlas. They are the multi-purpose experiments where we can do the fundamental proton-proton collision studies. And Alice was, you have already listened to the talk by Sanjeev. So he works on this experiment. And then LHCb is something like the matter, antimatter, asymmetry, and etc. that can be, or what we call in our language called flavor physics, that can be explored there, and that's designed for doing the flavor physics. Okay, the accelerator gets the particle gets accelerated in multiple steps. So, for example, it starts from the LINAC and then go to the first the booster, and then the proton synchrotron, then super proton synchrotron. By the way, when I told that Carlo Rubbia discovered W and Z boson, at that time he had to install this accelerator or this synchrotron, super proton synchrotron. And today we use it is in the chain of acceleration for the protons before putting them into the LHC ring. Okay, so that's how we recycle, and some of this proton synchrotron was also had some definitive fixed target and other things in mind when it was operational. So bit more here, and this is obviously under the 100 meters under the ground. And then the proton-proton collisions happened at 7 and 8 TeV in 2011, I mean till 2011 and 2012, that's called run 1. And run 2 is after that started in 2015, and where the center of mass is 13 TeV. Center of mass meaning what I mean, that I heard that Sanjeev was explaining, so I don't want to go. Each beam, if you sum them up in the center of mass frame, then you just get that energy. So when I talk about the square root of E, that means that's the total energy available for particle production. Okay, so it was initially 7 and 8 TeV, and now it's 13 TeV. Okay, till last year, and then when we resume in 2021, that time it would be 14 TeV, just 1 TeV higher. And why it is 7 and 8 TeV during run 1? Anybody knows? Why it didn't operate, let's say, even 13 TeV during run 1? When did LHC start? Do you know? For the very first time.
Don't have enough energy.
No. I'm asking, when was the first circulation of beam happened in the LHC tunnel? 2009, right? You want to change your answer? No, you are right. 2009, but there was some accident, and that's because if you have heard the accelerator talks, so this is the cryostats, so helium is inside there, and we are generating something like the field, something like 8 Tesla field, more than 8 Tesla field, and if the temperature goes little bit high, now imagine that the current, few thousand ampere current flowing, and superconductor becomes a normal conductor. what will happen? And that's the accident happened in 2009. And after that, it was the beam came back towards the end of 2010. We checked we did the real R&D that to make sure that no such accident, and what is the maximum energy, even though we had the sensor and etc. I mean, when I joined first time in the LHC in 2009, that time the accident happened, so I got little bit of time to understand, because before that I was working on the Tevatron. But the point there is that time I used to hear from the accelerator people that they absolutely made sure that the coinch protection system is very heavily, the tolerance level is set very low, and all the current connector splices were rechecked, and they did a recce, and they made sure that it's not more than 10 TeV is not very safe. That's why it was operated till 7 and 8. And then later, after the run 1, we changed all those splices, the connector splices, and then we can operate it now. Still we are not running at 14, but there is some other, actually right now those problems are not there. It's for a different reason we are operating at 13 TeV. Okay, so enough about the accelerators here. So, so let's see whether this video comes. Where is the video? Okay, so we talked about the Z boson, right? So and we talked about the protons. So if I consider the two protons at the LHC, they are colliding, and they collided in the Atlas collision hall. So I was in Atlas when the Higgs discovery happened. Then you have two of the the electrons and positrons that the Z boson decayed into. They came out, and this is the track. Okay, so you can see I established earlier or talked about the proton is nothing but 3 quarks, and here another 3 quarks. Then one of the quarks come here, and these are called, from the last talk, Feynman's name for these quarks and gluons jointly, even the fundamental particles, partons. That's right. So two of the proton partons come and they collide or they fuse together, then gets produced with the Z boson. Z boson instantaneously decays into electron and positron, and that's what we see in the detector. So that's the full picture if you want. This is already the known physics. Let's say before you were born, 84 color discovered. So everything is. If we are doing physics right, then we should first establish the physics that is very well known, and that's what.
Positron can annihilate.
Yeah, but they're the final state particles. They will interact with the detector here, and they're going in the opposite direction. Yeah, but they're not colliding, and that's exactly what was done in the LEP, Large Electron Positron Collider. There the electron and positron are collided together, they're fused and then produce the further new particles. So there it's an annihilation process. What happened now? No, I don't want that. Okay, let's go this one. Okay. Every time I bring it down. Anyway, so today I'm going to talk about the CMS detector simply because I am in CMS right now, although I was not there a few years ago. After coming back to India, I joined the CMS experiment from the Current Institute. And so what the CMS detector is very similar. So you have a beam pipe here through which the protons pass through. And then surrounding it, there is this tracker and pixel detectors, which are silicon based detectors. Surrounding it is the ECAL, which is the scintillator detector, lead tungsten, that I may have some time to talk about. And then you have the HCAL, which is the hadronic calorimeter, where so tracker is not a destructive instrument in the sense that you just measure the particle energy and the particle momentum, but while both the calorimeters, you remember from your earlier even high school lessons that the calorimeters are always absorb the energy, total energy, and you measure the total energy. So here the particle, by energy I mean the energy of the particle. So if you measure it, then the particle identity is lost. And then you have the outside, the muon system, where the muons can pass through all the way through it. And in between you have a magnet here which is 4 Tesla. 4 Tesla magnetic field it produces in this direction, that means along the beam axis. So the particle, the charged particle will have a trajectory according to its charge. And then the return field from here is caught through this red color things you can see. These are just iron blocks, so that you get the return field. Can you imagine how much is the current when I joined first time in CMS? How much time it passes through this one? When the magnet is on, you are not allowed to go actually close to magnet. Even people with the pacemakers, they cannot go underground at that time. But how much current can you guess? It's more than 10,000 amperes. And if the cryogenics fails, because it's superconducting one, and if the cryogenics fails, that the energy stored over there is going to burn everything. So we have a something like a thick grounding of this much from this one, just in case the quench mechanism fails, that to make sure that the current doesn't harm the detector. No, you just drain out the current, because so you have a thick copper, not foil, what should I say, block, continuous block of, you do the earthing here, right, but with a small wire, but there you'd be amazed, it's like this much thick and going something like few 200 meters or so, all the way from ground to somewhere else far connected. So anyway, so what do we detect here? So this is just the 1/4 of the thing. So muon, as I told earlier, so it's a charged particle. So that means it has to interact with the tracker and this one. It passes through in that path, and you get basically this trajectory. There is nothing that will happen here. Then next is that these are the stable particles that you can detect in the detector. Then this is the electron. So electron, it will have the bending, it has bent, and then in the electromagnetic calorimeter it will deposit its energy and get lost. It will not go further, and so you will get some hits in these layers and then the energy over here. Then you can have what? Charged hadrons like pions, for example. So they will have the trajectory here. They will have some deposition of energy in the ECAL, but not too much. There would be something, but okay, mostly it would be here. Then the next one is the neutral particle. So neutral hadron. It should only interact here and nothing over here, even though it passed through here. And that's what you see. Now you have the photon. What do you expect? It has to deposit all its energy over here, and that's what you see. There won't be any trajectory here, and that these are the stable particles that we can detect in the detector, and through these characteristics you can tell that okay, this is photon, this is charged hadrons, and so on. Although the hadrons, they after the quarks, they sort of get hadronized. It's a spray of hadrons, not a single hadron, and that means the pion shower that I showed here, or neutral hadron shower, there would be a concatenated or a kind of cone movement from one particular area, and that is after the quark hadronization. Okay, how big is the collaboration? CMS collaboration is quite big. You can see all the countries across the world, so you can say that sun never sets in the CMS territory. The same is true, by the way, in Atlas. Okay. So this is just a summary that these are the particles that we discussed, and these are the stable particles that we. Yeah, go ahead. What? You wanted to take a picture? You can Google. Okay, go ahead. Done. 1, 2, 3. Done. Okay, so what are the challenges? The challenges here at LHC is that, so this is the mass of the particle, and are you familiar with something called cross-section? Heard of cross-section?
Which probability of?
Probability. It's a probability that two particles they cross. For example, what is the cross-section, the differential cross-section for the Rutherford scattering? That I thought MS people they must have calculated. Rutherford scattering cross-section. Yes, classical way. What is the quantum mechanical calculation? What results does it give? That was the first thing I thought I was taught. Classically, you get for the Rutherford scattering cross-section, the whatever cross-section is 1 over sine to the power 4 theta by 2, right? And quantum mechanically, amazingly, it gives the same answer if you just do that. But the cross-section is the same idea. It's just like you have two things that crossing, and what is the probability of hitting. And that means now the cross-section names, it says that it's an area, the unit is of area. Even though we are talking about the probability, but unit is some kind of area, right? I mean, you can say the probability also in some ways that, okay, how much is the overlapping one, right? You can do some kind of change in parameters and things like that. So we represent cross-section in terms of area units, and for nuclear and particle physics we talk about something called Born, and Born is 10 to the power minus 24 centimeters square, minus 28 meters square. Okay, so this is what was, that means it represents some kind of probability that a proton crosses another proton at some energy, and what is the probability that this kind of event I will see, like BB bar or W or Z or even top quark, and then the standard model Higgs, and then Higgs to gamma gamma and so on, and then the new physics, something like scalar leptoquark and things like that. And the corresponding.
It's called scalar.
It's a leptoquark. It's supposed to be a scalar particle. That's why it's called scalar leptoquark. And you can have pseudoscalar and other things.
Why is scalar used?
Leptoquark, you just put in the model that it's I mean, you consider it to be a scalar particle, and then the model explains certain features beyond. These are all beyond standard model. This is beyond standard model. Everything is here the standard model, okay? And this is just new physics. So this is a new proposal that the big chart I showed, that something thought and something this direction. So somewhere you will find leptoquark there. So most of the collisions happened in LHC is the inelastic. That means inelastic meaning it's a ping pong ball. Ping pong ball? Is that so? That's elastic, right? Inelastic is something, not the overall this one, but something like single diffraction process, double diffraction process. Those kind of processes are called the inelastic processes, and they are quite high in number, but we do not want to look at those events actually. We are rather interested over here. We wanted to look at some exotic things, not the known physics. So, so typically if we have a luminosity of this kind, then inelastic cross section, inelastic cross section is around 70 millibarn, and that means you have this many interactions. But I cannot store all the events. Obviously, it's better that I store more and more, but I do not have infinite amount of data space. So I shrink it down, and then. But while shrinking, I have to make sure that I don't miss a single of these events, right? So that's what we do in the something called the trigger system. Like we say that, okay, there should be 2 photons. Okay, that could be a possible Higgs candidate. So trigger it and keep it. Don't throw it out. If the if the photon momentum is something like 5 GeV, obviously we might want to throw it out, because we know that if Higgs is decaying into photons, even with no energy Higgs produced, that means it will have half of the Higgs energy. So that means I will have something like 50-60 GeV of photon energy. So I want to filter that way, and depending on the final state, we try to keep all the interesting events from here to here into the storage disk. And remember that if I miss it from the trigger system, I cannot go back. If I somehow missed one event from here, I can never go back and then collect it. So I can, whatever I have stored, I can do offline analysis and always figure it out and do something to see whether it mimics some signature that I'm looking for. This I already talked about. So this is the number of observed events. If somebody asks you out of this talk that what is the femtobarn inverse, because the cross section is the femtobarn, right? Or burn, let's say. Then you multiply with the time period or integrate it over the time. That means, let's say from 2011 January to December I have collected, so I add them, and this is my LDT. And then I have the cross section for certain process, for example inelastic cross section, that's 70 millibarn. And then not all the inelastic events even my detector will see, or even I will throw out some of them in the trigger system. So if I just do this calculation, if I know this acceptance and the efficiency, then I should roughly know that how many such events were I should be expecting, right? So this comes from obviously from theory. So you can now generalize to any theory that this is the new physics cross section, and based on the final state you can guess how much would be the acceptance, and then further you know this number quite well, then you know how many such events are expected in that data set, right? So this is how the theorists basically also, when they propose a new theory, they first calculate, okay, so experimentalists are saying this much is the acceptance. I have my theoretical calculation giving this much cross section, and the luminosity I expect, they put some hypothetical numbers sometimes, like 3000 at femtobarn inverse, which is like end of LHC. And then they say that, okay, my theory would be established after this much data. You should be definitely able to see that and things like that. So that's this is an important formula that you should remember, and this is valid across the field. Anyway, so this is just the performance graph of the LHC or the CMS data taking. You can see from 2010 onwards, there's very tiny data set here, and then 11 and 12, I guess, yes, and then 15 here, 16, 17, 18. and we are, and you can see that gradually the curves are kind of getting steeper and steeper. That essentially means that LHC is operating extremely well, and in a quick time, LHC is delivering more and more luminosity, meaning, let's say Higgs or some other events, rare events, I will have much more probability to observe in these data sets than this one. Okay? And as I told, run 1 is this one, and run 2 we just finished last year, and then run 3 is going to start in 2021, and towards the end of my lecture there is this high luminosity LHC that I am going to talk about. Okay, so top quark. Well, when I was a PhD student, I started my career on the top quark, and this was, I think, when was the plot? This is not this here. I cannot see either. So it was discovered actually in 1995 by CDF and D0 experiments at Tevatron near Chicago. It's called Fermilab, and till the time we discovered the Higgs boson, it provided the most stringent limits on the Higgs mass. And this is explained here. It doesn't matter whether it's a recent or before, but here is the W mass, and here is the top mass, and the intersection that sort of predicts what is the expected, which Higgs mass is consistent with top quark and W boson mass. And that's because the theory has this kind of loops between the W top and here this one. So for top quark, we know that it's this +2,3 electron charge, and it participates in strong and electroweak production and decays. Actually, this is why top quark is very special. Top quark is the only quark that is decaying before the hadronization. Whatever you heard earlier this morning was the quarks get hadronized, right? And that happens at the time scale of 10 to the power minus 22 seconds. And top quark has a lifetime even smaller than that. So it decays. Immediately after the production, it immediately decays. So that gives the unique opportunity. That's the only quark where you can study the bare quark really at the bare level. I mean, bare meaning it's not bare in the sense that you can look at the decay products. So that's why it's special, and obviously before the Higgs discovery, it was the only quark that was constraining, because it's the heaviest one, and that's why it has the highest coupling with the Higgs, and that's why what we call Ukawa coupling and etc. So anyway, this is just for completeness. I put this figure, but I think you don't need to go through the details. So here, just to illustrate that these are some of the processes. For example, one quark coming from proton and another anti-quark coming from proton at LHC. In Tevatron, it was P bar or antiproton, so it was there, and then it gets annihilated through a gluon, and then gets produced into TT bar pair. And similarly, protons are enriched, and antiprotons are also enriched with the gluons, and they can also go this way, and there are other combinations that it can go. And then finally, one of the points that you should take home, take the message from here is that here we are colliding both at Tevatron and at LHC. We are colliding the hadrons, and they have constituent partons inside. So that means not all the momentum would be carried by this quark or that quark. So imagine you have a proton here which is 70 eV. You have another proton here which is 70 eV, but it's not guaranteed that these two will have 70 eV and 70 eV. It's a probabilistic process, because if you have three particles, or let's say energy of a system, three-body system, some number, that means it has to be shared by all three, right? It can go, one particle can go to really high level, that means the other two has to be zero, which is most unlikely. right? So this is what is the momentum fraction kind of. It represents that what would be the momentum fractions of the quarks and the gluons inside the proton based on different flavors at different energies. So these two are the experimentalists actually, these two are the guidelines to know how to tune the search and etc. for the top quark. And you should be expecting some, okay, this is the same story, I don't think I need to go. This is the electroweak production of the top quark. So for example, instead of quark here and then another one, but why electroweak? Because it's a W boson mediated here and so on. So that's why it's called electroweak. And the other case you saw only the strong interactions. Okay, then I told that it immediately decays. Now what it decays to? It decays 100% of the times into a T and B. I don't know whether you can see this one. So there is top and anti-top that gets produced. Then top decays into a bottom quark and a W plus. The anti-top quark decays into B bar and W minus. So this is 100% branching ratio. But then depending, and then W can decay subsequently in different ways, and that gives to different final states. For example, dilepton meaning the final state will have two leptons, two charged leptons. That's what is called dilepton. And similarly, lepton plus jets meaning it has one lepton. And jets is what? This bottom quark, I told you that they would be immediately hadronized, and then some of the hadrons, they will pass through the detector and you will see a spray of particles, and this is what we call jet. Okay, so that's why it's called lepton plus jets, and this is all jets meaning everything is jetty and etc. etc. And if you wanted, this is the total branching ratio for the TT bar pair. So now what is the key point from here? Okay, so this is like, I believe this is a dilepton event. Let me just double check. Yes, this is the photon and this is the muon. This is the electron and the muon. Yes. So this is an electron. This is a muon here, and this is the electron. I told you this is a real picture. By the way, the event happened in LHC at 0.5. That means at CMS at the time, July 14, 2016, 11 o'clock in the night, 45, 11 and blah 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 at GMT. So all this is real. Earlier I was talking about the simulation and so on, but this is real. And then in addition you will have other activities. So I told you that it's a dilepton, so that means that okay, there is a muon here, there is a electron here, that's you can see here, but then there should be some kind of missing neutrinos, right? And neutrinos we cannot detect in the detector. So whatever is the momentum imbalance, that we interpret as the neutrino measurement, and that goes here, and the two of the jets are here. You can see also some activities here. So this is the typical dilepton TT bar events. And then you can do the cross section measurement, and you can see this is the theoretical curve, this one. By the way, why there are two curves? Two curves because this is from the tevatron. This is the PP bar, proton antiproton collision and happening, and TT bar getting produced, and this one is the proton collision happening and the TT bar getting produced. So you can see this is the 7 TeV, this is 8 TeV, that's what LHC, and then you have bunch of measurements at 13 TeV. And tevatron on the way, it worked till 1.96 TeV, so it doesn't have any number here, that's why. So it stops there. So this is the measurement from RAN2. You can do all sorts of different measurements with the top quark, and simply because it's a bare quark that you can see before the hadronization, and with that you can do several measurements. Okay, so what about the masses? How good we are doing? So this is from the RAN1 meaning 2011, 2012. And this is the world combination. Remember, it was first discovered at tevatron. So tevatron has some data point which was bit off, and then the community kind of combined, I think I think this one and this one together. This is from the 2014, yes. So before that time there was whatever was the measurements from here and the Tevatron, this was combined there. But now the CMS measurement is the run one measurement is the most precise. Okay, so why it's required to be very precise? I told you the reason. Because along with the W mass, it constrains the Higgs mass. So if I know the top mass very precisely, then you remember one of the slides I had this curve in two axes and their cross section that I interpreted that's the Higgs mass to be seen. So similarly, there is something called VTB, vertex measurement, and that's over here. Okay, now what about Higgs physics? So Higgs physics is like we already discussed. The electron is very light and the top quark is very heavy, and the more the particle interacts with the Higgs boson, the heavier it is, and that's what it is. Now if you had called this guy as electron would have appeared heavy. Now it just happened that the particle that interacts with Higgs the least, we call that lepton as electron, and that's why it's electron. And so Higgs particle explains the mass of, and you can imagine that it's a field, and inside that you have to swim. And now you can imagine that, okay, you have a lattice structure here. If you have a very light, like thermocol kind of ball with some momentum, then it will change the direction, right? So that's exactly what is happening in case of in case of W, and photon obviously doesn't interact. And here you can see that the penguin you can associate with the electron, and over the ice it can slowly smoothly glide, and while the deers, they will be stuck obviously. And so Peter Higgs and François Englert and Braut postulated that because of this Higgs field, there should be a particle, physical particle, that's the Higgs boson, and this was postulated in 1964. And today, after 48 years, we found it. So they had to be really patient. And 2013 they got the Nobel, but they really had to wait for those many years, you can imagine. And Braut, by the way, did not get the Nobel for the reason that he died. Otherwise this Nobel would have been by the three people. Okay, so some similar kind of things, we have different names: glue fusion, vector boson fusion, and vector boson associated production, and then TTH. Okay, and you can see the same kind of structure that the initial partons are coming and then producing the thing. So the story is not remarkably different from the top diagrams that we are talking about. Only thing is that the Higgs, that means it has to respect all the couplings and so on appropriately, and accordingly all the cross sections and etc. would be changed. So if I go further, then Higgs decays into the fermions, the vector bosons, and then photons, and these we found actually these two channels at the discovery time, and later we are looking for this one, and there are different branching ratios that you can explore, that's according to the theory. And I just wanted to mention that, okay, since these two are the discovery channels back in 2012, so here there are two photons, you can see very clearly the Higgs is decaying. Well, you don't know where. I told you that you will not see in the tracker any trace for the photon, and you do not see any trace, right? So these are the photons that's coming out, that's detected actually here. This is just a display that how energetic they are, meaning it's just the magnitude on this axis just represents how energetic they are. And similarly, in the vector boson one, if the Higgs decays into two Z bosons, and then the Z bosons decay into two muons, each one of them, then you get this kind of picture. Then you get 1, 2, 3, 4 muons. Okay. So then this is the legacy measurement from run 1. So this is the theoretical curve. It should be around 1. And with respect to the theory, how good or bad we are doing. So this is representing that one. And this is the legacy measurement from run 1. And you can see that the particle mass and the corresponding coupling that we told that the massive the particle is, the interaction or the coupling would be higher. And indeed, through measurements we are finding, for example, muon is here and the top quark is here, WZ, then bottom and then tau. Okay. So these are all consistent results, but more precise things. And in run 2, I think I do not want to discuss too much there. The cross section would be a bit higher. So this is like 8 TeV versus just the cross section ratio. You get this kind of numbers, but you have other challenges experimentally. So as I told earlier, that if we have more cross section, that guarantees the more number of events, and that's the theoretical one. As soon as I move from here to here, but at the same time, I may have other kind of events that will also equally grow, right? So I will have more difficulty to find the number of events, the proportionate, if the cross sections are growing at the same level. So that's one point. And then in addition, from run 1 to here, so the LHC bunch crossing time, meaning one interaction happening, the next interaction is happening at 25 nanosecond interval. Earlier it was 15 nanosecond. Okay, so that makes the life much harder. And then finally, this is the key highlight from run 2, I think, so far, that one of the channels that was missing, that is the TTH, that means the TT bar plus Higgs. That means more and more energy is required, and that's why it's rare. And now we have observed, and this is also the standard model. According to the standard model, we should be able to observe, and we have observed now with the run 2. Okay, so Higgs coupling again revisited, and you can see that the muon, the mass scale here, because it's rare, that's why you get the error bar higher. Sorry? Okay, so dark matter, I don't think I want to bother you with the dark matter. So there are various ways. So for example, direct dark matter, you do this kind of way, like a standard model. So here is the sun, and then dark wind, it will have the effect, and then from there you can do the dark matter search. And then the indirect one is that like two dark matter annihilate somehow, and something happens that interactions we do not know, meaning it's dark simply because it doesn't participate in the strong interaction, it doesn't participate in the electromagnetic interaction, it doesn't participate in the weak interaction. Only gravity is there, and something in between that we do not know, maybe some forces or something, or interference between the two, or something that we do not know. That's why we represent it as a blob, because we are not drawing some patterns here. You see that. Huh? SM is the standard model particle. Standard model particle, like the electron and positron. So two of the dark matters, they get annihilated with some process that I do not know, and then I see two of the standard model particles, and that's what is there. And in collider, what do? We do just the opposite, meaning the two standard model particles we annihilate, and some mediation, something happens, and that again I do not know this part, but I do see some dark matter. By what do I mean by dark matter? That something completely escapes my detector, like neutrino at the moment. So, but I can calculate how much would be the neutrino background, and then what if there is some excess that I can attach that, okay, this is not explained by standard model neutrino processes, so this is something more than that. And that's how you can search in the collider, the dark matter. Okay, so then there are multiple ways. I think I do not want to get into that. But what does it mean? Remember, if it doesn't interact with my detector, then I will never see it. But how do I measure the neutrino momentum, for example, earlier? I was doing with some visible one, and we see in the transverse plane how much was missing, and that I was interpreting as the neutrino momentum, right? Now, if there is no activity like that clean process, like two dark matter, then everything would be balancing. I will not see anything, so there is no activity, but that doesn't help me, right? So I have to have some visible probe. So that's why these are called the ISR, meaning initial state radiation, like the standard model. For example, there could be a photon here or a jet here, a gluon here, and those kind of processes mediated by, and then they go to the dark matter. Then it makes sense. Then I'll find something imbalanced, and then at that point I will say that, okay, it's the dark matter. Okay, I think there are some limits. So at the moment, I think I just wanted to tell this one, that this is the spin independent and this is the spin dependent one, and some of the direct measurement processes, it comes here, and we are somewhere here. Okay, that's the difference. And if you consider actually the spin dependent one, then you get a different answer. That's the point. Okay, then what is the future? What you can do, or where you can help us? So as I told earlier, that we have collected the data up to this point. Now 2021 we will start here. That is called the round 3. Okay, and we'll get something like 300 femtobarn inverse the data. Okay. And that means it's almost double the so far the data we have collected, and that's by 2024. I think it's shifted now. Then we'll replace the detector, and then we'll have something called high luminosity LHC starting in 2026, and this would be the 14 TeV one. And there you can see it's one order of magnitude higher data set. And some theorists at the moment, for the rare theories, they always calculate this number, and that means, okay, this data collection will end something like 2034 or something, and at that point they are projected to be like that. So you can see that it's only the 3% of the data that is so far collected. Okay, then there are challenges in the run 2. Is high luminosity LHC, that right now we have, so pile up. What is pile up? I mentioned it very briefly there. That means I have a hard scattered event like top event or Higgs event or some rare process. But apart from that, each bunch, if you understand the collider, the accelerator, how it produces the bunches of protons, there are many protons in the bunches, right? And they cross, they collide, and then some hard scatter process happens. Apart from the hard scatter, there is other kind of processes that can take place, and here, because LHC will be much more number of protons there, these events can grow all the way to 114 and so on. So in phase 2, we will change the detector in various components. So the tracker, India is contributing. So Archana, she was talking about, she is doing something with this gem there. So that would be, some part is already installed and another part would be installed later. Then India is also contributing on this NCAP calorimeter upgrade. So these are the experimental contributions. So me personally, a bit biased on the tracker side, because I'm building some modules for the trackers in Bhubaneswar, and this would be shipped to CERN before 2024. SINP, Delhi University, then IOP, that's in Bhubaneswar, IIT Madras, and many other institutes are involved, but I think we will contribute the basic assembly of the detectors would be happening at Bhubaneswar in my institute. So with that, okay, so this is like why we need that one, and this would be the structure. For example, this would be the new geometry that would be operational at high luminosity LHC, and we are building actually these modules and then putting them in this ladder structure, and then finally in the detector it will go like this at CERN from 2024 onwards. Okay, so here are some numbers, I don't want to read it out. So to summarize, I think the particle physics is at the crucial juncture after the completion of the standard model, and I have convinced you, I hope. No collider signature for the BSM physics yet. Strong evidence for the dark matter from the earth that I also established or explained to you earlier. Then understanding the electroweak symmetry breaking and its consequences is just the beginning of a long journey, and we started that. And many more new results with improved statistical precision is expected during the LHC run 2 and beyond. And perhaps I can finish with Winston Churchill that this is not the end, obviously. This is not even the beginning of the end, but it is perhaps the end of the beginning. That means we have started. Okay? So with these words, I think I will stop here. Thank you so much for your attention. Questions, comments? Was it convincing, firstly? Or it was all Latin and Hebrew?